I guess we're recording now. Good. Okay. We're going to talk about the different parts of continental drift. The objectives are going to be summarize Wagner's theory, Wagner's hypothesis of continental drift, describe the process of seafloor spreading, identify how paleomagnetism provides support for the idea of seafloor spreading, and explain how seafloor spreading provides a mechanism for continental drift. Now, the idea of this chapter is we're going to talk a lot about the different theories that evolved into what we have for our plate tectonics theory now. What I call this is a progression of theories. We start with a simple theory, we build on that, keep the stuff that's good, get rid of the stuff that's bad, build on that to make it better over the years. That's exactly what happens. So we're going to start with Wagner's theory and end up where we end up with plate tectonics at the end. And you're going to have to need to keep track of that because there's going to be a big essay at the end of putting this all together in one big paper, basically, if you will. So let's start with summarizing Wagner's theory of continental drift. Wagner's hypothesis was that the continental drift, the hypothesis states that the continents were once one big landmass called Pangaea. That landmass broke apart, drifted to their present location. So his idea was that the continents just kind of drifted along the ocean floor. They're not drifting in the water, but they're just drifting on that ocean floor. Not a bad idea. It was first proposed by Wagner in 1912, and he has a bunch of evidence to support this. So it wasn't just he just said, "Oh, this will work," and then he came up with it. He had some stuff that did. First of all, he had fossil evidence. He looked at some plants and animals that could be found in certain areas of a continent. The only way they could have been found in those areas is if that continent was once connected to the other continent. We're talking about an ocean in between. So say, Africa and South America, and they went, okay. He looked at evidence from rock formations. Okay, we looked at the different rocks, and we talked about stratification, how rocks are laid down in an ocean bed or a river bed. And again, he's looking at that, and the only way they could have been put together is if they were laid down at the same time, so that stratification happened at the same time. Then he looked at climatic evidence, so talking about the climate, and he found that there were glacial striations in Africa, in the desert where it's hot. He found tropical plant fossils in Antarctica where it was cold. So obviously, somewhere along the way, those continents had to be in different spots or the weather was totally different in the world. Since we don't have evidence of the weather being different, those continents had to be in a spot that fit them more to the evidence of what the climate showed. Some of the obvious evidence, if you ever looked at a map of the world, it looks like the continents fit together, and that's where he started with this idea. He looked at the continents and said, oh, it looks like they all fit together, and then he found this other evidence that goes with it to help back up that idea. So here's a diagram where some of those fossils were found. The yellow or oranges shows a plant that's a tropical plant that was found in southern part of South America and in Africa and parts of Asia. And if you look, it looks like they all fit together. The blue is a mesosaurus, is an animal that you see a little picture of. This animal fossil stayed where it was, and we found that in different parts around the world where it only could have lived in those areas if they were together in a warm climate. He ran into some trouble. The idea that these continents were just plowing through the earth and the rock on the ocean floor was kind of ridiculous. It's like you trying to carry a 1,600-pound boat anchor and dragging it through the rock as the tide digs in. You really can't do it. And that's the whole idea of an anchor is to hold in place. And since these continents are anchored in place, people didn't like this idea. And they said, yeah, no. And they said he had to come up with some kind of mechanism, which he never did. He spent his life looking for it and never could come up with an answer for this question. So he had the evidence, but he didn't have the mechanism. So this goes into our first idea of what we're looking for the first step in that progression of theory, and that is that continental drift. The idea was that he had lots of evidence to back it up, that the continents were just floating around where they were. He had evidence from geologic, biologic, the different stuff we talked about, in that this is actually a climactic, and this is what happened. But since he couldn't come up with the mechanism, it fell apart. And that's going to be the first part of your essay, is explaining that. So why did many scientists reject Wagner's hypothesis of continental drift? I'll give you a minute to think about that. Actually, I guess I could ask you to hit pause so this doesn't just be blank. So hit pause, answer the question, then hit play. Here's your answer. Many scientists reject Wagner's hypothesis because the mechanism that he suggested was easily disproved. I mean, you could go out with a boat and drag an anchor across, and if you can't dig it across the ocean floor, then you got the same problem. One of the geologic features in the Atlantic Ocean we'll need to talk about is the mid-oceanic ridges. Mid-ocean ridge is a long undersea mountain chain, longest mountain in the world, has steep narrow valleys at its center that forms as magma rises from the asthenosphere and creates new ocean lithosphere as the plates move apart. We're going to talk a lot more about this in just a few slides, but one thing I want you to keep in mind when we're talking about this. Basically what's happened, there's a crack in the middle. As the plates move apart, it's like it's a volcano. When the plates move apart, magma wells up, fills that hole in the middle. Alright, it hardens into new rock. Do not make the mistake of thinking that the magma pushes the rocks apart. It does not. If you write that on your essay, you will be marked wrong. So the magma does not push the plates apart. The plates move apart, magma fills a hole. Not trying to be gross, but to give you an example, it's like if you rip a scab off your arm, blood fills that hole. That's basically what's happening with the mid-oceanic ridge. Okay? I know you're all going, ew, because I'm talking about blood. The reason the mid-oceanic ridge was found because a bunch of scientists in a ship called the Beagle were sent out to use sonar, which is a brand new technology, to map the ocean floor. They thought if they mapped the ocean floor, it would help with shipping lanes and things, and they thought they could make some money out of it. So as they're doing that, and they're mapping the ocean floor, they found that right in the middle is this huge mid-oceanic ridge. And they found two surprising trends that they were doing. They started taking samples, and they realized that there's sediments along the bottom, stuff that settles down to the bottom of the ocean. When you get up close to the ridge, there isn't much sediment. You get outside the ridge, way out towards the continents more, there's a lot more sediments. Meaning that, sediments are put down over time. Meaning that there wasn't as much time towards the center as there was out at the edges. The more time, the more sediments can settle there. So we're already getting our first evidence that this stuff up near the ridge is a lot younger. Speaking of that, the ocean floor is very young. When we look at rocks on land and we date them, they come out to about 3.8 billion years old. But yet, when we look at the mid-ocean or the ocean floor, the oldest rocks we could find were only about 190 million years old. That's with an M, not a B. So there's a whole lot younger than the other rocks we found on land. So again, there's something up. So as you look at those rocks close to the mid-oceanic ridge, they're younger, and the rocks formed from the ridge, from the outside the ridge, on the outside by the continents. And rocks close to the ridge are covered with less sediments than rocks further from the ridge. So again, less sediments up front, younger rocks up front by the ridge, get out to the edge of the continents, and you have that area where there's more sediments and the rocks are older.